we continue with Tomohiro Sasamoto that will talk about the one-dimensional KPZ equation and its universality.
Okay. Thank you for the introduction. First of all, I'd like to thank the organizers for giving me an opportunity to give a talk here today. I will talk about the KPZ equation, especially its one-dimensional version, based on collaborations with these people, Alexei Borodin, Ivan Tobin, Patrick Ferrari, Takashi Mamura, and Herbert Schwan. So, for the last few years, there have been considerable substantial progress in the understanding of the KPZ equation, especially in one dimension. And it seems that there will be several more talks and presentations for the KPZ equation during this conference. So my talk is intended for basically non-experts, so I will start from the beginning. So first I would like to talk about some basic properties of the KPZ equation, especially for the one-dimensional case. So I will start from explaining how does this KPZ equation look like, how that equation appears, and then first kind of non-trivial interesting question about the KPZ equation is that the KPZ equation is, as it is written as usual, not really well defined. But it's not so difficult to make sense of it, so I will explain that thing. And then in the recent developments about the KPZ equation, very nice features about this KPZ equation turned out to be that one can find very, very explicit formulas for some quantities of interest, for example, for the height distribution. And so I will explain about that. And especially in the limiting case, I mean, when t goes to infinity, where t is time, then we get trace rhythm distributions from random matrix theory, and this is very, very universal. And then I will also mention about what kind of structures behind the KPZ equation for the solvability of the problems. Recently, this is sometimes called the stochastic integrability, and I will mention a little bit. Then, for the last part, I will explain a little bit about the universality of the KPZ equation. There are several aspects of the universality related to the KPZ equation. Rather recently, when I was talking about the recent developments of the KPZ equation, he said that now it seems that the KPZ equation is everywhere. So somehow the KPZ equation, I think, in my opinion, the KPZ equation has been considered to be a very, very special topic in several senses. But recently, the robustness and the universality of the KPZ equation is getting more and more explicit. And there are more and more applications as well to various systems. So I will explain about these. Okay, so I start from the beginning. So the KPZ equation was introduced as a model equation to describe surface growth. So this is the physical phenomenon related, basically the physical phenomenon related to the KPZ equation. So of course there are various examples of surface growth, like paper combustion, bacteria colony, crystal growth. There are various examples, as you know. One motivation to study this kind of phenomena is coming from physics, especially statistical mechanics, especially non-equilibrium statistical mechanics. But there are several stochastic models, which as we are studying, and there are various interesting and non-trivial aspects from that point of view. This is basically our main interest here. And more recently, especially the one-dimensional case turned out to be related to other areas of mathematics, especially the theory of integral systems. and also representation theory. So by using the connection to these, we can study the KPZ equation and the related problems in great detail. Maybe it is useful to think about some specific simulation model to have an idea about what kind of things we are doing. So one example is called ballistic deposition. So we consider one-dimensional lattice like this. Maybe at the beginning, this is just flat. And randomly, in position, some box flows from the top. Maybe if there's nothing, then it just goes to the bottom place. But if there is an occupied site here, then it stops at here. So this is already a rule for surface growth, and maybe if you're a little bit good at computer programming, then you can do a simulation of this model. Then what you see is something like this. So this is x-axis, space axis. This is height axis. So we start from the flat initial condition. And then these are the three snapshots for the surface for this realization for time 10, 50, and 100. So at the beginning, there's no fluctuation because we started from the flat initial condition. But as time goes on, so there appears bigger and bigger fluctuations. And we are interested in these fluctuation properties of the surface, and especially how big is this fluctuation in this direction, and what kind of distributions it has for the fluctuation. And when t is large, especially, for example, for this ballistic deposition case, we see that the scale of the fluctuation of this height is given by t to the power beta, where beta is 1/3. If this is 1/2, in which case the scale, the fluctuation of the scale of the fluctuation is like square root of p, then you would expect that there is some kind of central limit theorem to have square root of t fluctuation. But in many examples of this type for surface growth, we see 1/3 exponent, and this is very, very characteristic for this KPZ type system. And we are interested in how this exponent appears and what kind of distributions this height has. One of the kind of most famous equation to describe, model equation to describe this surface growth is the KPZ equation, which was introduced by Kada, Paris, and San almost already 30 years ago. So let h of xt describe the height of position of x and the time t. Then the equation looks like this. So this is time derivative, this is diffusion term, and this is nonlinear term, depending on which is the square of the slope for the height. And there's also noise term eta, which is assumed to be Gaussian with mean 0 and covariance given by this delta function in both x and t direction. Okay, so this is the famous KPZ equation, but how does it appear? There will be several ways of explaining, but here I would like to explain like this. So suppose you want to have some kind of description for the surface growth. Maybe the simplest way you're describing would be to take just a diffusion equation. This means that if there's some bump in the surface, it will smoothen after a while. So in that sense, this may be a kind of simplest description of the surface. But this is not enough for our purpose, of course, because this is a deterministic equation. So in that sense, there's no fluctuation. So this is not enough. But then maybe we can add some noise term to this diffusion equation, like this, where eta is Gaussian noise with zero mean and covariance in there. So white noise eta. And this is already well-known equation, known as Edwards-Wilkinson equation. And this also already has non-trivial properties, but this is not enough for our purpose, because this does not give the correct exponent, especially the one-third exponent which I explained in the previous slide. So then you have to think about what kind of other aspects you have to take into account for describing the surface growth. And one simple way is to realize that although we are conscious, maybe it's better to explain on the blackboard. So our height is defined in this direction. So this is space axis, and this is height axis. So the surface may look like this. So it grows basically in this direction, perpendicular to the surface, but we are measuring the height in this direction. So we have to think about this geometrical effect. Then if you assume that the slope is not so large, then maybe you can expand this effect like this. Then what you get as the biggest contribution is the square of the slope of the surface. And if you think that this is relevant for the description of the surface growth, and put it in the equation, then what you get is the KPZ equation. Of course, once you get the equation, then you don't really assume that this slope, this dx of h slope is really small. So we accept it as a given equation. Okay, and the first thing these three people, Parizan and Sam, did for this equation is to apply the kind of physical renormalization group argument. And they found, for example, for the case of one dimension, that the exponent beta is given by 1/3. So this is consistent with many simulations. And this shows that there is some strong universality associated with this kind of surface growth phenomenon. And because this exponent was captured by this equation, this universality is usually called KPZ universality graphs now. And we are basically interested in this universal behavior for the surface. So now we have this equation, and I will explain the details, but there is a simple scaling for this equation. So we have three parameters in front of each term, lambda, nu, d. But by a simple scaling, we can eliminate these, and we can put them to be some specific value, which we take to be nu equal 1/2, lambda equal d equal 1. So the equation, the KPZ equation we will be treating in the following is this, rather than this generic one. Okay. To study the KPZ equation, one useful thing is to consider the cold-hot transformation, which is given by this. This is very, very simple transformation, right? So the original variable is h, height function, and then we simply consider exponential of that height function, which we call z. And if you do a simple calculation using usual rules of the derivatives, then what you get from the KPZ equation for this quantity z is given by this. So you see that this equation is linear in z, so this is a very big simplification of the problem, at least it seems. But one difficulty is that eta was originally as an additive noise in the KPZ equation, but for this case, this is appearing as multiplicative noise. So we have to be a little bit careful, but still this is linear. And in fact, this has a nice interpretation, because this you can think of as a kind of one particle problem. So this is imaginary. This can be considered as one imaginary time Schrödinger equation for one particle with random potential eta. So in other words, this can be also thought of as a problem of polymer in random environment eta. Can you Can you see this? What I'm drawing there is something like this. So we are considering polymer starting from some point and any at some point, and there is a potential eta like this. And in the language of the polymer, one natural initial condition is the delta function, which means that we consider polymer starting from the origin. And what is the corresponding initial condition for the KPZ equation? So then you have to think about this called Hopf transformation. Then you see that this delta function may be thought of as a limiting case of e to the power minus absolute value of x. So this is a kind of wedge for the surface. But we take delta goes in 0 in a limit. So this means that language of the KPZ equation, this initial condition corresponds to this very, very narrow wedge. And this is, technically, this is the simplest case. Okay. Now let me explain a little bit about the difficulty for the KPZ equation. So the equation I showed you here contains eta, and this is not really good for mathematical purposes, but usually in this kind of case, we may replace this eta by dEdt. And then more mathematically well-posed version of this equation would be given by something like this, which is called the stochastic heat equation. But one thing one has to be careful is the meaning of this product. Okay. Sorry. So, and here B of xt is considered to be cylindrical Brownian motion with covariance given by delta in x. The question is, what is this product? So I mentioned that when we get the stochastic heat equation from the KPZ equation, we use the usual way of differentiation, which means that this product should be considered as Stratonovich, which is usually denoted by this circle dot. But there's a simple translation from between Stratonovich and Ito. Then what happens if we want to have this equation in Ito sense? Then we use the usual translation like this. So this is Ito product, and there's an extra term like this. The problem is that if you compare this and this equation, then you get product of dB with the same argument x and x. Because we are considering cylindrical Brownian motion with delta x minus x prime, if you put x prime equal x, then we have delta of 0, which should be considered as infinite. So this is the kind of difficulty for defining the KPZ equation. But this is the kind of the problem of well-definedness for the KPZ equation, and this can be kind of cured by a simple means, because this equation with Ito interpretation for this product is well-defined. So then maybe we can define the solution of the KPZ equation by the inverse of the Hopf transformation of this well-defined quantity z, log of z. And this is the well-defined version of the KPZ equation, known as Hopf solution for the KPZ equation. So in a sense, then the KPZ equation, the well-defined version of the KPZ equation may be written as this, with this minus infinity, but this is just one way of writing it. So this is one way of defining the KPZ equation, but this you have to use some nonlinear transformation called Hopf transformation. Of course, it would be nicer to have a well-defined version of the KPZ equation without this kind of transformation. And in fact, Martin Heyer found such a way, and he may talk about this during this conference. I don't know. Now come to the explicit formula for the one-dimensional KPZ equation. I think the kind of simplest nice formula for this kind of story is given by this. So this was discovered by myself and Herbert Schwann, and basically at the same time by Amir Cohen Cluster. So we consider the KPZ equation or the stochastic heat equation with this initial condition. So delta initial condition for the polymer or the narrow wedge initial condition for the KPZ equation. And then what we found is that, so this bracket means the expectation value. And we consider exponential to the power h with some additional shifting and parameter s. Then this expectation value can be written as single Fredholm determinant. Here, gamma d means t over 2 to the power 1/3, and this Fredholm corner is given by this expression, which is an integral of two area functions with this kind of deformation, deformation of simple product. So this is the formula, the example for the simple formula. This is for the generating function for h. Actually, this is basically equivalent to having this explicit distribution function for h. And this can be written like this. So this is the equality in distribution. So this is a subtraction of the deterministic part, and there's a kind of deterministic shift as well. But the most non-trivial part of the about most important information about the fluctuation of the height is contained in this random variable Ct, and the distribution function for this Ct can be written like this. This is the formula we found at the beginning. So this can be obtained by the formula which I showed you in a previous slide. So they look very similar, I think, even though this looks slightly more complicated. But anyway, once we have explicit formula for the height distribution, we can, for example, draw the distribution by plotting. Okay. For example, we can compare with some numerical simulations. And when t goes to infinity, this curve approaches some limiting shape, and it turns out that it is given by the trace rhythm distribution from random matrix theory. And of course, this you can show by explicit calculations. Maybe most of you already know about this distribution, but maybe in one slide I would like to explain a little bit about this. So these distributions appear in the theory of random matrices, which is an ensemble of matrices with random elements. And there are several special random matrix ensembles. The kind of most important one is the GUE, Gaussian unitary ensemble, which is an ensemble of n by n Hermitian matrices, and whose density for the matrix is given by this e to the power trace of h squared. And dh is a simple Lebesgue measure for matrix elements. And then the non-trivial point for this GUE is that you can obtain explicit joint distribution for the eigenvalues of which are denoted by x1, x2, blah, 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 xn. And the expression is given by this, where delta of x is given by the van der Monde determinant, and there also appears some simple product of Gaussians. Once you have this expression, then you can also think about several properties about distribution, statistical properties for the eigenvalues of GUE. Maybe you can think about largest eigenvalue of the GUE random matrix, and if you scale in this way, then you see that this distribution goes to some limiting distribution, which is denoted by F2 of S here, and this is the GUE type trace rhythm distribution. And it is also known that this can be written as single Fredholm determinant, where the Fredholm kernel is given by this simple product of area functions. And this distribution is the one appearing as a t goes to infinity limit for this KPZ distribution. So this means that even though the KPZ problem and the random matrix problem may look completely different and separate, in the t goes to infinity limit, they have the common distributions. I think this is really non-trivial discovery. But then, about random matrix theory, I also would like to mention that there's also GOE trace-rhythm distribution, which is denoted by F1 function for GOE, which is a Gaussian orthogonal ensembles, which is an ensemble of real symmetric matrices. So GOE is for Hermitian matrices, and GOE is for real symmetric matrices. Okay, sorry. So these are, maybe you cannot see, but I plotted the probability densities for GOE and GOE trace-rhythm distributions. Okay, so that formula was nice, but how do you derive them? One way of deriving the formula is by using the replica approach. So as I mentioned, the KPZ problem can be reformulated as a polymer problem, from which you can get Feynman-Katz expression for the partial function z, like this. And you see that eta, which is the randomness, appears in the exponent of exponential. Then you should remember that eta is Gaussian noise. So you can take the Gaussian average at the beginning for this moment for the partition function z. So in this case, you prepare n polymers for the same randomness. So this is called replica partition function. And you can take average with respect to eta to get some non-random problem. And in this case, for the case of the KPZ equation, this non-random problem turns out to be given by this Hamiltonian for the delta Gaussian. So this is Hamiltonian for n particles in one dimension. So this is free part, and there's an interaction among particles, which is given by a delta function. And this is called delta Gaussian. And once you get this formula, so this is the quantity we are interested in, and you first expand this in terms of this moment. And now we use the fact that this delta Gaussian is known as kind of one of the simplest integrable systems, and we can use some knowledge from integrable systems to study this quantity. And then by using the integrability or in more explicit way, Bethe-Anders method, in this case, then we can get some expression for this replica partition function. And then you plug that expression, then see that actually this summation can be taken to give a single Fredholm determinant, which I showed you in a previous slide. But here, there's one thing we have to be careful, which is that this replica partition function behaves like e to the power nq as n becomes large. And if you think of putting this, substituting this expression here, you immediately see that this summation is not convergent. So there's a difficulty in this computation. But actually, afterwards it turned out that we can think about regularized version of this calculation, which I explain a little bit from now. Okay, the KPZ equation is an equation for in continuous space and time, but there are some difficulties, like this or the other well-definedness for the KPZ equation. But maybe we can think about some discretized model, and one of the nicest example is the ASEP, asymmetric simple exclusion process. In the one-dimensional case, we consider this kind of system. So each particle tries to do asymmetric random walk with weight p to the right and q to the left. And the exclusion interaction among particles, so this particle cannot hop to the right, this particle cannot hop to the left. If particles hop only in one direction, this is called tacep, totally acep. And the quantity we are interested in for this acep is the integrated current. So we count the number of particles which pass this bond between sites x and x plus 1 up to time t. So this is not instantaneous current, but this is integrated current. And in fact, there is a simple mapping between this kind of particle system and the surface growth problem. Just replace an empty site by this upward slope and occupied site by this downward slope. Then particle configuration can be translated to surface configuration, and particle hopping can be thought of as a local growth for surface. And then in this mapping, this integrated current for acep becomes actually the height for the surface height. And it is actually known that this surface growth model also belongs to the KPZ equation. And in fact, actually, if you take certain weakly asymmetric limit for this acep, then one can get the KPZ equation. So by studying the acep and taking this weakly asymmetric limit, actually we can study the KPZ equation as well. Okay. There's also another nice discretization of the KPZ equation. So one is called Q-tacep. So tacep is an acep in which particles hop only in one direction. So this is a generalization of usual tacep. And in this case, particles hop in one direction and only to the right neighbor. This is the same as the tacep, but the hopping rate depends on the particle distance in front of that. So as I'm writing here, the rate is given by 1 minus q to the power the distance between particles. So this can be also used as a discretization of the KPZ equation. There's very related model, which is Q totally asymmetric zero-energy process. So in this Q-tacep, consider the dynamics of the distance of particles, gaps, rather than the particle position. Then you can think about some different dynamics. And actually this can be considered as some zero-energy process with hopping rate 1 minus q to the power number of particles. And this is called Q-tazarp. And this is also thought of as a discretization of the KPZ equation. And we can also think about similar quantity as for acep, integrated current. And then for both acep and Q-tacep or Q-tazarp, one can think about the endpoint function like q to the power current, like this. Then one can see that this quantity, specific quantity, satisfies n particle dynamics of the same process. So maybe we are thinking about the infinite number of particles in the original process, but if you consider this specific quantity, then endpoint function behaves like n particle problem in the same process. So this is basically the same as the self-duality of the process. This is the generalization of the well-known duality for symmetric simple exclusion process, in fact. This is actually discrete generalization of the delta Bose gap for KPZ. And then one can apply the same replica approach to this discretized version without any mathematical difficulty. So this can be considered as a rigorous version of the replica method for the KPZ equation. And in other words, so the replica approach for the KPZ equation, which I explained a little bit in the previous slides, can be thought of as a shadow of the rigorous version of the replica approach for this KPZ problem. And with also Petrov, Rao, we also considered more kind of generic branch-layer theorem for this process, and there will be more generalizations to come soon. And so I was explaining these kind of developments only for the case of wedge case, but there are various generalizations and developments. One thing about such generalization is the flat case, which has been done only by using replica, I think. So the flat case is considered to be one of the important examples in the studies of surface growth. So this is the case which I showed you for the ballistic deposition, right? And in this case, it turned out that the limiting distribution is given by GOE trace rhythm distribution, F1 of S. So there is a geometry dependence for the limiting distribution. Maybe the exponents, 1/3 is the same for both wedge case and the flat case. But if you also think about the distribution, the limiting distribution, then they are actually different. So the universality for the KPZ equation is kind of subdivided into sub-universality classes. I don't think we have really, we don't have really precise understanding of this division of the universality class into subclasses, but this is one nice example, I think. And one can also study multi-point case. And I'm not explaining really the stochastic, how and why such nice formulas can be found for the KPZ equation, but I would like to just mention that behind this structurability there's integrability, especially the quantum integrability for studying the KPZ equation. And I don't explain here, but afterwards, there are more connections were found from the KPZ equation to integral systems. So there are some connections to quantum tonalities, the XZ spin chain, and also some Macdonald processes. And I expect Ivan Kopin will tell you more about this connection. Okay, talking about one generalization, maybe I would like to mention that one can also study the stationary case, which means that for the case of KPZ equation, the Brownian motion is stationary. So if you take as initial condition for H, two-sided Brownian motion, this is a stationary situation. So this is a snapshot for t equals 0, and this is a snapshot for some later time t. And we are interested in the correlation between these 2 points. For example, we can apply the replica method to study the correlation for the slope. So we showed that this can be written in a rather explicit form, which is a little bit involved, so I am not really showing. But by using that formula, for example, we can draw the figure for this 2-point function, which is like this. This is one example. So lastly, I would like to mention a little bit about the universality. So I said that in the t goes to infinity limit, we get, for the height distribution, the trace rhythm distribution from random matrix theory. So this is considered to be very, very universal. As a simplest example of universality, of course, you all know that central limit theorem is the kind of statement for the universality. So if you consider any independent random variables, then the sum over n behaves like the Gaussian variable. So this is central limit theorem. And the question is, what kind of generalizations can we have for example, the trace rhythm distributions? And the understanding of universality of this trace rhythm distribution from the context of random matrix theory have been developed to some extent. So there are some kind of moment conditions on which you can show the trace rhythm limiting distribution. But from the point of view of this surface growth or directed polymer, our understanding of the universality is much less satisfactory. So this is, I think, still a very big open question in our community. But here I would like to mention only 2 examples for universality. One thing is that actually we can see this universality in real experiments. So you remember that the original motivation for the introduction of the KPZ equation was to describe surface growth. And it's also about 4 years ago, Takeuchi and Sano from Tokyo University, they invented a nice way of preparing some surface growth system and measured the height distribution for this system. So they use two modes or phases of liquid crystal turbulences. And first they put some voltage to prepare the system in one mode, and then at time t equals 0, they shoot the laser beam here, which is taken to be the origin, and from that time on, the second phase grows like this. Then they can measure the surface by using CCD camera, and then they measure the fluctuation of the surface. By using some lens, they can also study this flat case, which is typical for surface growth. And here, what they are showing here is that if they measure the exponent, they are just given by 1/3, which I explained already. So this already shows a strong universality for the exponent. But because their experience was so good, they also study the distribution itself for this surface growth, and they found good agreements with the trace-rhythm distributions. So the left-hand side is for circular case. So this is GUE distribution, and the right-hand side is GOE distribution for the flat case. So you see also in the experiment, real experiments, that there is a strong geometry dependence in the limiting distributions. So this is a strong evidence for the universality in nature. And as the last point, maybe I would like to mention another universality, which is a kind of hot topic recently. So I showed you for the case single component, the 2-point function can be also studied. And recently, there is an interesting conjecture by Bailey and Schwann, which says that this scaled KPZ 2-point function would appear in rather generic one-dimensional component systems, which means that it should also include one-dimensional Hamiltonian dynamics, which is deterministic, not stochastic. The KPZ equation is of course a stochastic system for one component system, but this conjecture says that maybe the same scaling behaviors would appear for deterministic process and also for multi-component systems. I cannot explain the details, but okay, for example, I just show you this figure. So the conjecture is very general, so maybe you can think about some Hamiltonian dynamics with the shoulder potential given by, with the potential given by this. Then maybe you can see, but you see some peaks like this. Actually, I cannot, sorry. Okay. And actually, this is the same as this figure for the single component KPZ. So this is for the deterministic dynamics. So if you really, so this is of course just a molecular dynamics simulations. Of course, we are interested in proving that mathematically, but this seems very difficult now. Maybe it is a little bit easier to think about the stochastic model. So for example, we also consider the two-component version of the asymmetric exclusion process called AHR model, in which there are plus and minus particles with these dynamics. And in this case, there are only two conserved quantities. And by using simulations, we could also see this single component KPZ scaling function for this case. So this might be already very difficult, but there's a better chance than the Hamiltonian dynamics to prove this, I think. Okay, this is basically also, I was only explaining the case of one-dimensional case, but there are recently renewed interest in higher dimensional case. I have not done anything, but recently there was a nice recent Monte Carlo simulation in higher dimension, especially in 2 dimension, helping heal this Monte Carlo simulation for two-dimensional directed polymer systems, and he observed some kind of limiting universal distributions depending on the geometry. So we don't know how we can study or if we can study this system at all, but it seems true that there are some universal behaviors in two-dimensional case and maybe in more high-dimensional case, and this would be a very, very interesting question, I think. So to summarize, I started from the explanation about the basics of the KPZ equation related to surface growth, and I also explained the explicit formulas for KPZ equation, and this is which is related to integrability of the process, and I also explained a little bit about the strong universality of the KPZ equation. Okay. Thank you for your attention.